All right, so we've got a table of values for f and f prime for some function that we know is a differentiable function. And we want to use a left Riemann sum, 3 intervals of equal length, to approximate the length of the graph of f on the interval from 1 to 7. So the integral that we need to set up is an integral from 1 to 7 of the square root of 1 plus f prime of x dx, right? Because that's the formula for the arc length. So this is the integral we're going to approximate. And so first thing we need to do is just start plugging in these values of f prime from at 1, at 3, and at 5, since we're using a left Riemann sum, to figure out what this ends up being. So if we're going to start at 1, the length of that first interval ought to be 2. So it ought to be 2 times the square root of 1 plus f prime of 1. I don't know why I made that so big. So 1 plus, oh, sorry, this is supposed to be squared. Forgot to square that. That's what somebody just said in the chat there. So that should be 1 plus 4. Let's see. Yeah, that's what somebody said in the chat. So 2 times 1 plus 4 square rooted, plus then the next one is again 3 to 5, length of 2, times the square root of 1 plus then f prime of 3 is 1. So 1 squared is 1. And then we should end up with plus 2 times the square root of 1 plus f prime of 5, which is 0 squared, which is 0. And that ought to give us 2 root 5 plus 2 root 2 plus 2, which looks like it's choice D. Does that make sense to everybody? Cool. Yeah, no problem. Other questions? What else we got? That's literally the only question. You all went through all of those multiple choice questions from the old practice tests, and you all successfully did every single one of them. That's spectacular. You're all ready for the test. We can end right now if that's the case. All right. Nobody else has any questions from those? If you don't, I mean, we'll start doing some other stuff that I've got. Yeah, I can review the ratio test and the nth term test just in general, sure. So the nth term test, and it doesn't just have to be problems, it can just be anything in particular you want me to talk about. So the nth term test is a test solely for divergence. And the nth term test says that if you have a series, well, I'll say for the series of a sub n, if the limit as n approaches infinity of a sub n does not equal 0, then this series diverges, guaranteed. That is all there is to the nth term test for divergence. That if you have a series and the limit as n approaches infinity of that nth term is not 0, it will diverge. If that limit as n approaches infinity of a sub n equals 0, then a sub n might converge or it might diverge. So it doesn't tell you if something converges, it can only tell you if something diverges. That's why we call it the nth term test for divergence. Good with that one? That makes sense? Yeah. Okay. And then we'll talk about the ratio test also here real quick. Yeah, Derek, you do not need to know the reduction formulas. That is correct. I mean, if you want to know them, it might be helpful, but any of the problems that they give you that you could use a reduction formula for, you could always just use the power reducing formula as well. So. All right, our ratio test. A ratio test is, it's going to tell you what the interval of convergence for some function is, or whether it converges or not, or for some series. So the ratio test says take the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. Okay. And in order to do this, we need to have all positive terms, which is why we, in case our series does not have all positive terms, that's why we throw it inside of an absolute value to make sure that the series has all positive terms. And remember that if you prove that something has absolute convergence, that means that it does have convergence, and that it also converges. So what we do with this is we will take the limit as n approaches infinity. If this is less than 1, it converges. If this is greater than 1, it diverges. And if this is equal to 1, it is inconclusive, and we don't know which one it does. And so there's two different situations where you might use the ratio test. If you use the ratio test on something that does not include any x values in it whatsoever, when you look for this limit, you're just going to end up getting some number that will, tell you pretty obviously if it converges or not, or if it's inconclusive. Right. So if you do this and there's no x values in here, you're not looking at a specific power series, and it comes out to be, a half, well, it converges. If it comes out to be 7, well, it diverges. And if it comes out to be 1, you got to find another test. But when we do this with a power series, we might come down and end up with something like the absolute value of, I don't know, something like the absolute value of 2x minus 4 is your limit, or something like that. Well, depend whether that's less than 1, greater than 1, or equal to 1 depends on the value of x. And so you just need to set that limit that you get less than 1, and then you should be able to figure out for what values this converges. So in this case, we just rewrite it as 2x minus 4 is less than 1, greater than -1, and then you can, solve down for your interval of convergence, add your 4, and you divide by your 2. And if they want to know what is the radius of convergence of something like this, if you're looking just for the radius of convergence, you can go in and you can factor that 2 out. So you get 2 times the absolute value of x minus 2 is less than 1. Then you can divide by that 2 to get absolute value of x minus 2 is less than a half. And so you know that your radius of convergence there is just a half. And then, you could solve this inequality to get, it's between 5 halves and 3 halves, which is the same thing you'd get if you did this one. But this way, you need to get it down to just absolute value of x minus a is less than r, where r is your radius of convergence. Does that help, Mahika? Cool. All right. Other questions that you all might have, whether it's problem or just something in general? All right, number 28 from the 2015 multiple choice. So give me a second to pull that up. Okay.
No, this is still down. Where are you? Oh my God. How are you gonna finish? Adam, you're still back at the game.
Apparently my kids' friends are bad at video games. All right, I'm looking at this one, right? So we've got, let's read through. We got f that has derivatives of all orders for all real numbers. Piece of 3 is our third degree Taylor polynomial for f about x equals 0. We know that the Taylor series for f at 0 converges at 1. And we know that the nth derivative of f is always less than or equal to n over n plus 1 between 1 and 4. And all values of x as well. Oh, What? Oh, okay. Sorry. You're good, Derek? Not on this one, obviously, but you were going to be the next thing I talked about, so never mind. All right. Okay. And we want to know which is the smallest value of k for which the Lagrange error bound guarantees that f of 1 minus the third degree Taylor polynomial at 1 is less than or equal to k. So f of 1 minus the third degree Taylor polynomial at 1, this is our error. So we're really just looking at, our error, and our error is just less than or equal to, always, the n plus first derivative times, our x value, which in this case is going to be 1 to the n. So, we've got our n plus first derivative. Let's write this better. N plus first derivative at x, where x is some value between 1 and 4. And then times 1 to the, since we're doing third degree, 1 to the 4th over our 4 factorial. And since we're talking about values between 1 and 4, the largest value that this can come out to be, if we plug in values into n over n plus 1, between 1 and 4, if we look at 1 over 1 plus 1 is a half, right? And the next one would be 2 over 3. Next one would be plus sign there. If you use 3, you'd have 3/4. If you had 4, it'd be 4/5. So you want to choose whichever one of those between 1 and 4 there is the largest possible value. The largest possible value is 4/5. So we end up with 4/5 times, 4/5 times 1 to the 4th, which is 1. So times 1 over 4 factorial, which looks like that is choice B. Does that make sense to everybody? Cool. Other questions? Said just in general, or any questions from any of the free response that I've posted, any of the multiple choice, or the free response from those full-length tests? You can also ask from any of those extra multiple choice packets that I put up online in the Google Classroom. That's fine too. All right. Well, if you come up with other questions, let me know, and I will move away from what we will now be doing. So sounds like we are running out of questions. Let's take a look at a couple of series. I feel like series would probably be the best place to look at some extra free response questions. What do you guys think? Does that seem reasonable to you? Okay. Cool. So I'm just going to start here. Actually, I'm going to just start at the very last one that we've got here. So this may or may not be one that you have looked at. This is from the My AP Classroom stuff. So I'll give you guys a second to just sort of read through it, and then we'll just work through it together and see how we can do. So it's got 4 parts here with a Maclaurin series. Cool. All right, yeah, Ben, I saw yours. So after we do this problem, I'll go back and do that one you're asking about. If in 10 minutes or 5 minutes when we're done with this problem, I've forgotten, just yell at me and tell me that we need to. All right, so part A of this, you all got a chance to at least read the first part there. Part A wants us to get the first 4 non-zero terms and the general term for G. And so G is just f of x squared. So all we should be doing here is just taking the function for f and replacing every x in it with an x squared. So our first term ought to be x squared instead of x. Our next term ought to be minus x to the 6th over the 3 factorial. Next term ought to be plus x to the 10th over the 5 factorial. And the 4th one ought to be x to the 14th over 7 factorial. Everybody good with that? For the first 4 non-zero terms? And then for the general term, you'd want to put in -1 to the n, and then your x is becoming an x squared, so it's x squared to the 2n plus 1, so you can multiply those powers together. So that should become x to the 4n plus 2, and then all over still that 2n plus 1 factorial. Part A, good? I hope. Okay. Part B. So part B is just asking us to find this limit. Limit as x approaches 0 of x squared minus x to the 6th over 6 minus g of x over x to the 10th. Okay, so first off, when we try to plug in 0 to this numerator is going to be 0 minus g of 0. Well, what's g of 0? G of 0 is f of 0. And f of 0, if you plug in a 0 for all these x's, also looks like it's going to be 0. So that whole numerator should be 0 over x to the 10th, which is 0 over 0. So the determinant. But before we start really dealing with that, let's see if we can simplify down this numerator, this x squared minus x to the 6th over 6 minus g of x. That should look like x squared minus x to the 6th over 6 minus, and then all of this, right? X squared minus x to the 6th over, well, that's 6, plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, plus this -1 to the n x to the 4n plus 2 over our 2n plus 1 factorial. And we still are going to be over, you can see that, over x to the 10th. And so as we simplify this down a bit, we should be able to see if the x squareds cancel, the x to the 6th over 6 and the positive x to the 6th over 6 should cancel out. And so then we're left with x to the 10th over, or let's say negative x to the 10th over 5 factorial. And then we're going to add to it this same series, right? And the reason we're going to pull the x to the 10th over the 5 factorial out is because that can be divided by this x to the 10th. So I'm going to rewrite this as negative x to the 10th over 5 factorial. And then I'm going to say, well, then the rest of it is just that same series, except instead of starting at n equals 1 or 0, whatever they had us starting at before, what value are we starting at here to get the, what was it, the x to the, I forgot what it was, but it was x to some largish power over there, 14th or something like that. Yeah, to get to the x to the 14th over our 7 factorial, what value do we need to start at? We need to start at n equals not n equals 6, should be n equals 3, because n equals 3 is going to give us a power of 14 here. We're at x to the 4n plus 2. And this is still all over x to the 10th. Yeah, now it's not a good time to forget how to do math here. That's okay. You got till, right, you got like 16 hours, what, 20 hours, 19 and a half hours. So you got to remember how to do it. So now we're looking at this, and what does this give us here? The negative x to the 10th over the 5 factorial divided by the x to the 10th ought to be what? That ought to just be negative 1 over 5 factorial. And then plus, if I throw in the divided by x to the 10th to all of this, what does that make this? This becomes the series from n equals 3 to infinity. Limited x approaches 0 here. N equals 3 to infinity of negative 1 to the n plus 1. X to the, well, 4n plus 2 over x to the 10 ought to be 4n minus 8. And then still over 2n plus 1 factorial. And if we're looking at this as x goes towards 0, well, this is negative 1 over 5 factorial. And then this, as x goes towards 0, well, this is still going to become, starting at n equals 3, this will still be an x to the 4th here, and then everything else will be a larger power than that. And so I have 0 times negative 1 to the n plus 1 over 2n plus 1 factorial. 0 divided by all that stuff and multiply by that stuff is still 0. So we end up with negative 1 over 5 factorial, or negative 1 over 120. Good or no? That one makes sense to everybody? I hope. Cool. Yes, this is a non-calculator problem. In fact, the series questions are all non-calculator questions. I've not seen one in the past 20 years that has been a calculator question. And there's nothing that's guaranteed that it will be a non-calculator, but like I said, it has been problem number 6 every year since, I believe, the last free response questions I have from BC is like 1998. And it has been free response question number 6 every year since then. So let's see here. Part C is h is the function, the integral from 0 to x of g of t. We want to write the first 4 non-zero terms and the general term for h, and then we want to use that, the first 2 terms, to approximate h of 1. So we're going to integrate our, we'll just say h of x is the integral from 0 to x of g of t. And so I'm going to write out g of t just in its general form here. I think it was t squared minus t to the 6th over 3 factorial. I'm just going to put it in terms of t because of the x there. You can use any variable you want, but normally, as you've noted, we always use t. So t to the 10th over 5 factorial minus t to the 14th over 7 factorial, I believe. Does that sound right? And then negative 1 to the n t to the, what was it, 4n plus 2 over 2n plus 1 factorial. And so what I'm going to do is I'm just going to do my term-by-term integration. T squared is going to become t cubed over 3. I'm going to evaluate that at x. I'll create my dt. So that'll become x cubed over 3. And then that'll become minus x to the 7th over 7 times my 3 factorial. And then plus x to the 11th over 11 times my 5 factorial. And minus x to the 15th over my 15 times my 7 factorial. And then my general term ought to stay as, that was n plus 1, I think, wasn't it? Or was it just n? No, it was just n. I don't know why I thought it was n plus 1. Okay. So the negative 1 to the n will just stay. And then we'll have x to the 4n plus 3 over 4n plus 3 times our 2n plus 1 factorial. And then technically we should be subtracting this thing evaluated at 0 also, but note that all of these terms are just going to be zeros. So this is my first 4 and my general. Everybody good with that part of part C? And I believe, what did they ask us to evaluate it at? Was it, I think it was 1? Does that sound right? Was it 1? Yeah, h of 1. Okay. So h of 1, and they said to approximate it using the first 2 terms, I believe. So that'll just be, we'll put approximately equal to 1/3 minus 1 over 7. Well, we'll just write it out as 1 over 42 because that's 7 times 6. And then what does that come out to be? If we get a common denominator there, that's going to be 42 multiplied by 14. So that's 14 40-seconds minus 1 40-second, which ought to be 13. Everybody good there with part C? And then part D, we want to know why that approximation that we found in part C differs from the true value of h of 1 by less than 1 over 1,000. And so this one, we should note that what is this series doing, our series for h? It is going from positive term to negative term to positive term to negative term, right? Negative 1 to the n, right? H is alternating, and therefore use the alternating series error bound on it. And the alternating series error bound should just tell us that the error, so our value, the true value of h of 1 minus our approximation, the absolute value of that ought to be less than the next term after where we truncated. The next term after where we truncated was x to the 11th over 11 times 5 factorial. And our x value is 1, so it ought to be 1 to the 11th over 11 times 5 factorial. And the annoying thing here is we're going to have to actually evaluate out what that is to show that it is less than 1/1000th. What is 5 factorial is 120, and 11 times 120 ought to be 1320. So 1 over 1,320, which is less than 1 over 1,000. And therefore, since we know the area of the error is less than 1/1320th, it must be less than 1/1000th as well. Everybody go to part D there? Cool. All right, and then somebody's asking me to go back to part B. Is this part B? I think this was part B. Was the limit? Yeah. Did you have a question on that, Mahika, or you just wanted to look at it for a second? Okay. You good now? All right. Cool. So let's see. Ben, you were asking for something. I gotta go back in here. What was like? Was it an area volume one? Yeah, area and volume. FRQ number 3, part D. All right, give me 1 second to bring that up. Now I'm not sure which area and volume one you're talking about, because the number 3 I've got here doesn't have a part D in it. What are is it a polar area in volume 1, Ben?
Yeah, it's actually the first one that we did on Friday. I realized that I had a question about it.
Okay, that's the one with like regions R and S?
Yeah, that one.
Okay, cool. This one, yeah?
Right, yeah.
Okay, what was your question there on part D?
I know what we're trying to find the theta, because we found, I think, WA in the previous, I think, in C.
Yeah.
And I know what needs to happen, but I don't know how to do it with my calculator.
Oh, okay. All right. So let me just refresh my memory. Let me look at it for a second, because now it's been a whole day, 2 days since I did this one. So what were we doing? We were looking for the distance between the two of them. So it was G minus F. Does that sound right? Yeah. And we were trying to figure out, so we had 2 cosine theta minus 1 plus sine theta cosine 2 theta. That was W, right? And using the information in part C, find the value of theta for which W of theta equals the average value. And so we found the average value in part C, is that right? Okay, so we want to know, when does this equal the average value? Does anybody happen to remember what the average value was? Or do you have it in front of you, Ben?
Yeah, I believe it was 0.485.
0.485, okay. Yeah, so all you need to do to figure out when 2 cosine theta minus 1 plus sine theta cosine 2 theta is equal to 0.485. Is that the part that you're having trouble with, or is it the second part, figuring out if it's increasing or decreasing at that value?
No, the first part.
The first part, okay. So I can't really show you on the actual graphing calculator here, but we can do it on Desmos. All you need to do is just open up your graphing calculator. And let's see, oh, what was it? 2 cosine theta minus 1, and then it'll be a minus sine, and then cosine 2x. Is that the right function?
We can't see Desmos right now if you're on it.
Oh, well, then it's hard for you to tell me. Is that the right function now? 2 cosine x minus 1 minus sine x cosine 2x.
Yeah.
Yep. Okay. So all you need to do is just graph that, and then you need to just graph, what was it, 0.485? Is that what we said? I need to, oh, here, I gotta make it equal to y. And so we're just looking for where those intersect, and those intersect at 0.518, it looks like. Is that the value we used in class? I don't have the scoring guidelines up for this one because I wasn't looking at it. Is that the value we had? Yeah.
Yeah.
Yep. So that's all. You just graph this function, graph this one, or alternatively, if you don't want to graph 2 different functions, you can just subtract the 0.485 and look for where it crosses through the x-axis. That's just a max there, yeah. So at 0.518 also.
Okay, gotcha. Is there any reason why we would need to switch our calculator to polar mode?
No, there shouldn't be. I mean, you could. I mean, I guess you could. I mean, you could do this in polar. Yeah, I mean, you could do it in polar, but there's no real reason to, because you just want to know when does 2 cosine of theta minus 1 plus sine theta cosine 2 theta equal 0.485. And so, I mean, you can, I mean, doesn't matter what variables you use, you should be able to just put it in terms of x and y and just graph it. I mean, you might want to put it into polar mode just to, like, if they gave you, if they gave you an equation or 2 equations and you weren't quite sure what they looked like and it was the calculator section, I mean, I'd put it in polar and graph them then, but other than that, there's no real reason to.
Okay, gotcha. Thank you.
Cool. All right. Other questions that people might have on anything before I go back to, let's see, was a question, Ryan, for the limit comparison test, if the value you get as your limit is between 0 and infinity, it means that the series, but both series must converge or diverge. That is correct, yeah. So if you do the limit comparison test, and if the value is between 0 and infinity, then they either both converge or both diverge. That is true. And real quickly, since we're talking about this, you'll note, hopefully, somewhere down here, here it is. So in Google Classroom, right down here, BC test reminders, just somewhere down there in that stream. This has literally got like all of that kind of stuff. You know, basically how you do everything. And somewhere in here is there it is the limit comparison test. So yeah, you're welcome to ask me, obviously, also, but you know, this should have all the different tests that you need to know and the conditions that are required for each of those tests, and then what usually it's a limit that you're looking for, what that limit equals and what that tells you about the series. Wait, there it is right there. So I highly recommend that if you have not been going through that document in the last couple of days, that you read through it all and think, not just read it, but like think about what it's saying as you go through for each of those tests, and really for everything in that document. It's only It's only like, I don't know, 14 pages long or something. Yes, exactly right. So if you use the limit comparison test, you need to show that the one that the one that you're comparing your series to either converges or diverges to prove that yours does too. Yep. So you gotta have some reasoning, and usually you'll use, if you're talking about the series of like 2n squared over 8n cubed plus 1. Well, since it's n squared over n cubed, you'll want to compare it to 1 over n, and then since you know that 1 over n diverges, as long as you get a real number for that limit, which you will, you'll know that they both diverge. Does that make sense? Cool. Other questions? Sure, the Lagrange error bound. So I'm just going to use, there was one that we just, oh no, it was that last one with the multiple choice that we just did. So the Lagrange error bound literally just says that the error after if you truncate the polynomial into n terms, the error, I'll make a new page for this, but the error using Lagrange error bound. So if I truncate after, n values, then the error, which is the nth degree Taylor polynomial at x minus the true value of the function at x, should always be less than f's n plus first derivative evaluated at some c value, where c is between x and a, and x, remember, is whatever value we're evaluating it at, and a is the value that our series is centered at. So, if it's a Maclaurin series, a is 0. If it's not a Maclaurin series, a may be something different. Times x minus a to the n plus 1 over n plus 1 factorial. So effectively, it is the next term, because this is generally the next term, except that that next term, we're actually taking that derivative piece of it and evaluating it at the value between x and a that makes this piece right here the largest it could possibly be. Does that make sense? So when we look back at this previous one here, we truncated at 3 terms, so we used x to the 4th over 4 factorial, since we truncated at 3 terms, and then we used the derivative at some value, and they're giving us values between 1 and 4 here. Obviously we're going to use 4 because 4 is giving us a larger value here, and so 4 over 4, and we're at 4 because our third degree Taylor polynomial. So 4 over 4 plus 1 is 4/5 times the 1 over the 4 factorial. Does that make sense? Anybody else have any other questions on the Lagrange error bound? The 2 right-hand pieces of this should be pretty easy to figure out. I mean, those are just, your x minus a to the next power, and this is just your n plus 1 factorial. This is the piece, the n plus first derivative at c, that's sometimes difficult to find. Generally, they will give you some information like this, where the derivative is always n over n plus 1, or less than or equal to that. Or they'll say that n plus first derivative is always less than or equal to some specific value, or they might say, if it was this problem, they might say the fourth derivative of f is always less than or equal to 7. Well, then you put a 7 in there. Or they might give you a function, for example, like sine of x. Well, if f of x is sine of x, well, what do you know about the derivatives of sine of x? They're always, no matter what degree you go to, they're always less than or equal to 1. And when you put it in an absolute value, this is also in an absolute value. They're always less than or equal to 1, greater than or equal to 0. And so the largest possible value will always be 1 up here, or something like sine x or cosine x. Or if they gave you something like, e to the x, well, that the largest possible value of this is just e to the x, right? So you pick your largest x value on your interval, and that's the value that you put in there. If they gave you something like e to the 2x, and you're talking about the third derivative, well, the first derivative would be 2e to the 2x, the second derivative would be 4e to the 2x, the third derivative would be 8e to the 2x. So you know that the largest possible value of this derivative is 8 times e to the 2x power, where your x is whatever whatever value you got that's largest. It makes it the largest on your interval. Does that make sense? Does that help? Hopefully that makes sense and is helpful to everybody. Cool. All right. I think I've answered all the questions that were in the chat. Any other questions, or else we'll go and do another one of these series FRQs. Give you guys a second to see if you got anything.
So, okay, so A is the value that the series, converges around, and X is where we're actually solving it.
Yeah, X is what we're approximating the value at. A is the the center of your series. So like when they tell you right here that it's about Taylor series about x equals 0, tells us that value, that A value is 0. And when it says f of 1 and third degree Taylor polynomial at 1, tells us that we're looking at a value of x equals 1. So here we'd have to be picking the value between 0 and 1. I mean, it doesn't matter for our case here because they are just telling us that no matter what, for all values, for all the in values between 1 and 4, which is what we're using is an in value of 4, that we need this to be the largest possible thing. But yes, in this example, A would be 0 and x would be 1 from this. And we didn't need the Lagrange error bound way down here with whichever one we were doing. But if let's say we were doing it for this series for H, well, we know that it's we know that it was centered around x equals 0. So our A value would be 0, and then our x value would be 1 if we were using the Lagrange error bound for this particular one, which we're not. But does that make sense?
Yep, thank you.
Yep. Any other questions, anybody? Okay. For e to the 2x, would the Taylor polynomial be 1 plus 2x plus 2? I'm not quite. I'm trying to understand what your question here is, Ryan. I understand the first one, e to the 2x, around 0. So let me put in a new page here so that everybody can sort of see what we're talking about here. So e to the 2x, the Taylor polynomial. If you're approximating the Taylor polynomial for that, it'd be this is f, right? F of, suppose we're going around 0. F of 0 is 1. F prime of 0 is 2 e to the 0. That's 2. F double prime of 0 would be 4 e to the 2x, so 4, and so on. So yeah, to answer your question, if you're trying to do the one for e to the 2x, yes, it would be 1 plus 2 times x over 1 factorial plus 4 times x squared over 2 factorial. So I think that's what you had, the quantity 2x squared over 2 factorial. Yeah. And so you just did yours from just doing the series for e to the 2x, right? Which is fine, but this comes out to be exactly the same. But I'm not sure what the second one you're asking. You're saying e squared to the x. that what you're asking about? Oh, e to the x squared. Okay, yeah. So e to the x squared means that you take your series for x and you replace all of the x values with x squared values. So your regular series for e to the x is just 1 plus x squared over 2 factorial, right? Plus x cubed over 3 factorial, and so on. So if you're doing e to the x squared, that'll become 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 3 factorial, which I'm not sure if that's what you wrote, but that's what it should be. 1 plus x squared plus x. Yeah, it looks like that's what you wrote. Yep, that's exactly right. Yep. It's just like, yeah, you just throw it in. You can change any series that you know the values for to any other one that is similar to that by, if you have sine of x, you can make it sine of x squared by just replacing the x's with x squareds and so on for any other series that you've got. That is perfectly fine. You could also do e to the x squared by taking the derivatives. You could, e to the 0 would be 1, and then the first derivative of this would be e to the x squared times 2x, which if you evaluate that at 0, right, is just going to give you that's just going to give you 0. Oh, yeah, 0 because I have an x term there, right? So that becomes 1 plus 0x. Then you'd have to take the derivative of this using the product rule, and you'd end up with a 1 as your value, and you'd have a 1x. You'd end up with a 2 as your value because you'd end up with 1x squared over 2 factorial, and so on. It'd come out the same. But this way is much easier. Hold on 1 second. All right, and then let's see, Noah, you were asking something here. Are there ever any problems where the value of C is not either A or X? It's possible. Usually it's going to be one of those two endpoints, I would say. I would say 90% of that time it would be one of those two endpoints. Does that help? I mean, I would say chances are that it's going to be one of the two endpoints of the interval. All right. Other questions that you all might have? If not, we'll do another series FRQ. Yeah, no, sorry, my kid was having an issue with something, so sorry, I was muted there for a second. Yeah, we can do a partial fraction decomposition one, is actually PFD, or an improper integral one. Yeah, we can do that, and then we'll come back and do another series one. Let's see here. I got some of those in here. Just gonna find one. Okay, let's do this one. It's an area of volume but it's also yeah, this has also got an improper integral. So let's do this one. Cool. I'll give you guys a second to read through it, and then we'll work on it together. No, apparently I was muted. I was trying to talk to you, but apparently I was muted. Cool. Yeah, sorry. I was helping my kid with something. I don't know. He's having some issues. We all ready to do this one? All read through it. Makes sense what we're trying to do. Cool. All right. So for part A here, we're just looking for the area of region R. And region R is just going from 1 to k. So first off, we'll just integrate our function, which was 1 over x dx from 1 to k, which should be pretty straightforward. Natural log absolute value x from 1 to k, which ought to give us natural log of k minus natural log of 1, which ought to just give us natural log of k. Part A should be not as straightforward as these problems come. Okay. Part B, they want us to find an expression for the perimeter of region R. So first off, to find the perimeter, we need to find all of these different values. And first value here, this ought to be the y value at x equals 1. So that's just 1 over 1. And then plus the distance from 1 to k, which ought to be k minus 1. And then this distance here, which is the y value at k, which ought to be 1 over k. And a lot of people forget to do all of these little regions, not all these little regions, but all these little pieces when they're doing the perimeter. I don't know why, but for some reason people do. And then the last thing we need to do is the integral from 1 to k of the square root of 1 plus f prime, and f prime is negative 1 over x squared dx. And don't forget the squared like I tried to do earlier today on the negative 1 over x squared on that derivative. And so if you want to simplify it down, you got k plus 1 over k plus the integral from 1 to k of the square root of 1 plus 1 over x to the 4th dx. And they didn't ask us to evaluate, so we don't need to. Good or no? All right, cool. So then for part C, which is the part where you get yourself an improper integral, part C, we're going to take region R and rotate it about the x-axis to form a solid. And then we're going to talk about as k increases without bounds, so k is going towards infinity, find the volume of that solid or show that that volume is infinite. And so I will tell you this right off the bat. it's fine for you to say this, pi times the integral from 1 to infinity of your function squared, right? We need to do it squared because we're revolving around the x-axis. And so 1 over x squared dx, 1 over x, the quantity 1 over x squared is 1 over x squared. And the reason we're squaring it, right, is pi times the radius squared for the circular cross sections. And so it's fine to write it like this. It's good to write it like this. But if you do not rewrite this as the limit as some constant approaches infinity, and then you put your pi on front if you want, or you can put your pi in between. It doesn't really matter. Of the integral from 1 to a, and I'm just going to, just for the fun of it, right, this is x to the -2 dx. If you don't rewrite it as a limit, you will not get any of the points for an improper integral on the AP test. So make sure that you always, 100% of the time, if it's an improper integral, you can put the infinity in the limit to begin with, but rewrite it as a limit afterwards, or you get nothing for anything that you've done. So then this becomes pi times the limit as a approaches infinity. Integral of 1 over x squared, or x to the -2, is just -1 over x from 1 to a. And so we'll have pi times negative, my limit, pi times the limit as a approaches infinity of -1 over a minus -1 over 1. And -1 over infinity is 0. Negative of 1 is 1. And pi times that 1 is just pi. And so we would show that it is a finite value. Finite volume there is pi. And this is one, this is the one we talked about in class. Gabriel's Torricelli's trumpet. Is that good? Does that help you there, Noah? Does that answer your question about what you wanted to see? Great. Sure, I can show parts A and B for like 5 seconds. 1, 2, 3, 4, 5. You're good now? Okay. Any other questions in particular people want to talk about? Sure. How about this one with polar area? That is the page that I'm already on. That one look good to you, Ben? Perfect. All right. So this will be our next one. I'll give you guys a second there to read it, at least the first part, figure out the graphs are and see what we're trying to do, and then we'll move through it. Okay, so we got two circles here. We got cosine theta and we got 2 sine theta. Which one's which? Should know that cosine theta is the one in the first and the fourth quadrants, and sine theta is the one in the first and the second quadrants. Obviously, this one should be bigger because of the 2 in front of it. Cool. So first thing it's asking us to do is to find the area of region S, which is the overlap there between the 2 different curves. So first thing we're going to have to do, and this one, by the way, is a calculator problem. I didn't see it first. This is a calculator problem. So first thing we need to do is figure out where cosine theta and 2 sine theta intersect with each other. So we'll set cosine theta equal to 2 sine theta and determine that that happens at theta is approximately 0.46368. And then so now that we know that, we just need to integrate the first one, the 2 sine theta one, our bigger circle, from 0, because that's where we start here, to where they intersect, right? If I plug in 0 for theta, I start at 0, 0. So I should just plug in 0 and then go to that intersection point. And we should have our 1/2 out in front. So 1/2 the integral from 0 to, I'm going to just name this as capital A, so I don't have to keep rewriting it, which is acceptable for you to do on the AP test. And I highly recommend it on a calculator question anyway. So integral from 0 to A of 2 sine theta squared d theta. And then we will add to that the area from our A value to pi over 2 for the other one, which, at A is where we get here, and then we're coming around until we get to pi over 2. And we hit pi over 2 on this, cosine of pi over 2 is 0, so we're back at the pole. So A to pi over 2 of cosine squared theta d theta. And that should be your integral. Oh, and it asks us to evaluate it, right? To actually find the area. So what does that come out to be? Let me see here. Looks like that comes out to be looks like it's 0.240. Everybody good with part A there?
Sorry, can you explain the second integral?
Yeah. So the second one is from here to here. The value at that C value where they intersect to the value of this circle when theta is pi over 2. So this is this integral. And then I should have probably done a different color here, but then this is that integral.
Okay, got it.
It's because it's straight along this line, theta equals 0.463648 is where we're switching from one function to the other function, being the bound of that region. Does that make sense?
Right, okay, yeah.
Cool. Any other questions there on part A? All right, part B. What is part B saying to us here? Part B says there's a point on the graph of R2, so 2 sine theta, where the slope of the line tangent to the graph is tangent to 2. At this point, dx d theta is 2 cosine 2. Find dy d theta at this point. Well, that should be pretty easy, I hope. We know that dy dx, which is the slope, should be, what was it, tangent of 2? And dy dx is equal to dy d theta over dx d theta. So really, we've got tangent of 2 is equal to, which one did they give us? They gave us dx d theta. So dy d theta over 2 cosine 2. And so all we have to do then is solve for dy d theta. And looks like that tells us that dy d theta would just need to be 2 sine of 2. That way the 2's cancel, and the sine of 2 over the cosine of 2 gives us tangent of 2. So 2 sine of 2, since you have a calculator, you can approximate that out if you wish. It's fine to leave it as 2 sine of 2 also, though. But it approximates out to 1.819. Everybody good there with part B? All right, part C, we got a new polar curve r of theta, which is cosine theta plus 2 sine theta. We're going to find the greatest distance from any point on the graph of r to the origin. So first off, it's, what is it? No, it's 2 sine theta plus cosine theta. Is that right? Is that the right function? We don't know. Yeah. 2 sine theta plus cosine theta. Cool. All right, so we want to know the greatest distance from any point on the graph to the origin. And so all we need to do then is, recognize that this function r equals 2 sine theta plus cosine theta represents, this is the distance from the origin to the function. I mean, that's what a polar coordinate is. It's a straight line from the origin to that polar equation. So we want to know when is this for, I believe it said for 0 to pi. Yeah, for 0 to pi, when is this at a max? So we need to find r prime. R prime ought to be negative, not negative, it should be 2 cosine theta. And then minus, excuse me, minus sine of theta. And we will then figure out when that's equal to 0. And when is that equal to 0? At least on the interval between 0 and pi. When does 2 cosine theta minus sine theta equal 0? When does 2 cosine theta equal sine theta? Looks like that's theta is 1.107149. And we can't be guaranteed that that's a max. We're not for sure that that's a max. So what do we need to do? We either need to make a sign chart to prove that it's a max. So we'll put on 1.107149 and plug in something greater than that, or in something less than that. So if I plug in something less than that, let's say like pi over 6. Pi over 6 is definitely less than 1. Plug that in. The cosine of pi over 6 is what? Cosine of pi over 6 is root 3 over 2. So this becomes root 3 minus a half. Well, the square root of 3 minus a half is definitely positive. So we're increasing to this point. And then we'll check and make sure that we're decreasing afterwards. So going all the way up to pi, we gotta just plug in something that's less than pi. We'll put a 0 here too. And plug in something that's greater than 1.107. So I don't know, you could put in, I don't know, what do you want to put, 3 pi over 4 or something like that. That's definitely more than 1. So 3 pi over 4, 2 cosine of 3 pi over 4 is, what is that? That's 2. And then the cosine of 3 pi over 4 is negative root 2 over 2. And then we've got minus sine of that. So that's minus root 2 over 2. And so we, clearly this is going to be a negative minus some positive. That's clearly going to be negative, which tells us the functions are decreasing. So we know it's a max at that value. I don't know, did it ask us for the actual max or just the location where it occurs? Yeah, find the greatest distance. And so it's very important to make sure that you note that this is where the greatest distance occurs. And then you'll need to figure out what is 2 sine, we'll call this capital B since we already used a capital A. So 2 sine of capital B plus cosine of capital B, just because I don't want to rewrite them. That's our actual maximum distance. And that comes out to be 2.236 with some other decimals. That's our actual value. Good or no? Is that a good one? I don't remember who asked for a polar one, but
I actually had 2 questions. When calculating the derivative of r, when can you just do it the way we did, and when do you have to break it up into the x and y components, multiply one by cosine, one by sine, and then do the derivative that way?
That's a good question. So it depends on what the question is asking. This question wants to know when is r at a max. And so if we just have some function, r equals whatever in terms of whatever variable, right? It doesn't matter, it doesn't matter what all these variables all are, as long as it's something equals something else in terms of one variable, right? Because then this is just a rectangular, basically it's just a rectangular equation, right? It's a function that represents a distance between two things. And we want that distance to be the max. So we just take the derivative of r with respect to the variable that we're using, theta. So r prime is just this derivative. It would be the same as if we rewrote this. We could totally just rewrite this as y equals 2 sine x plus cosine x and say, when is that at a max? Well, I mean, then the process we'd use would be to take the derivative of this with respect to x and set it equals 0, right? So that's when we do that. But when we're talking specifically about an equation, a polar equation, and we want to know what its, the slope of its tangent line is, the slope of the tangent line of anything is always dy dx. So if it's written as r equals, something in terms of theta, you've got to break that down then to find the slope of the tangent line into its components of, y equals r sine theta and x equals r cosine theta, and then do the dy dx that way. Does that make sense?
Okay, got it. Thank you.
Mm-hmm. And then let's see. Somebody's asking here, the two integrals in part A represent the area bounded by the two curves and theta equals 0.463. Well, not quite. That they represent the fact that these two things intersect at 0.463. And so I can go from 0 to this 0.463 value on my first curve cosine, because I'm sorry, not on my cosine, but on my first curve of 2 sine theta, because on 2 sine theta, the stuff below the green line is all, it's all part of this larger circle, and it's from the origin to this point at 0.463, where if I plug in 0 to 2 sine theta, I start at 0, right? Sine of 0 is 0, so the radius at 0 is 0, which tells me I'm at the pole. So I'm going from 0 to the value at 0.463. Well, the value at 0.463, to get to there, we trace along the outside of this curve. And the area is always a straight line directly in from wherever you are on the curve to the pole. And so until we get up to here, that can all be included as just that piece. That piece that's below that line. And then for the red piece, it's just this piece of cosine theta starting at 0.463, coming around till when I get to cosine of pi over 2, which is 0, which tells me I'm back at the pole. And so that's all the stuff above that green line. Does that make sense? Does that answer your question, Ryan? Yeah. Cool. All right. Everybody feel okay about that one now? Okay, let's do, what do we think? What do we think? Another series one? What do we think about that? Yeah? I feel like usually we want to do the series ones. How about this series one? It's got a Lagrange error bound. So I know how much you all love Lagrange error bounds. What do we think? Does that look like a good one? Cool. Take a second to read through it, and then we'll start working on it.
so bad.
Okay, so we are looking at the series 2 to the k over 2 to the k over 3k times x to the k. So first thing that we want to do here is find the fifth derivative of f at 0. So in order to find our fifth derivative of f at 0, we should just need to think about what the terms of this series are when we get out to the to that fifth term. So if it's x to the fifth, use a different color here. If it's x to the fifth, then we should have a fifth derivative at 0 in front of it, and we should have a 5 factorial down here, right? That should be that term that is included with our x to the fifth. And so all we need to do is figure out what it is here. And when we plug it in here, it should be x to the fifth times 2 to the fifth over 3 times 5. And so if we want to know what is the fifth derivative of f at 0, we can get rid of these x to the fifth, and then we just need to solve for the fifth derivative of f at 0. And so it looks like if we do that, we'll end up with 2 to the fifth times 5 factorial over 15. We should be able to simplify that down. This ought to become, let's see, we can get rid of the 5 and the 3 to cancel with the 15. That leaves us the 4 and a 2, which is 8. So we got 8 times 2 to the fifth, which is 8 times 32, which ought to be 256. So we just equate what we know the fifth term should be by using a Taylor polynomial with what we know that same fifth term should be by plugging in a 5 into this series. Does that make sense, everyone? Cool. All right, part B wants us to use the ratio test to find the interval of convergence for f about x equals 0. So if we're going to use the ratio test, I'll start it here, but we'll probably need another page. We're going to do the limit as n approaches infinity of the n plus first term, or in this case, I guess the k plus first term, over the kth term. And we'll put it all inside of absolute values, because for all values of x, this is not always positive. So we'll have 2 to the k plus, that plus 1 up there, 2 to the k plus 1, x to the k plus 1, over 3 times k plus 1, times the reciprocal of this. So that ought to give me a 3k up here. It ought to give me a 2 to the k down here, and it ought to give me an x to the k down here also. Everybody good with the setup using the ratio test? Hopefully. And then we can see what all simplifies out of this. This ends up being a limit, and I don't know why I put in, since we're doing k, we should have k goes towards infinity here. The 2 to the k plus 1 over the 2 to the k is just a 2. The x to the k plus 1 over the x to the k is just an x. And then we have a 3k, and we have a 3k plus 3 down there in the denominator. And as k goes towards infinity, the 3k over the 3k plus 3 is just 1, and we just end up with the absolute value of 2x. So if we want to know when does this converge, we take our limit and make it less than 1 according to the ratio test. We'll take the 2 out of this and divide, so we end up with the absolute value of x is less than a half, which tells us that our radius of convergence is a half, and that the interior of our interval of convergence is from a half to negative a half. And then you have to go back in, and you're going to have to test this series both at negative a half and at positive a half. It doesn't specifically talk about showing when it has absolute convergence and conditional convergence and all of that. So we don't have to worry about those. We just need to worry about if it converges at a half and at negative a half. So at x equals, we'll start with negative a half, I guess. At x equals negative a half, this series begins to look like, well, the series is k equals 1 to infinity of 2 to the k over 3k times negative 1/2 to the k. And we should be able to simplify that down. The negative 1/2 to the k could become negative 1 to the k and a half to the k. So we end up with a sum from k equals 1 to infinity of negative 1 to the k, and then 2 to the k times a half to the k. Well, those are both being raised to the same power, right? And 2 to the k and a half to the k, those are going to just cancel each other out, right? There's a 2 to the k in the numerator and a 2 to the k in the denominator. And then in the denominator there, we have a 3k still. And what do we know about this? We know that this is an alternating series and that the terms are decreasing in absolute value towards 0. And therefore, this converges by the alternating series test. Everybody good with the first part there for at x equals negative a half? Okay. So then we'll test it at x equals positive a half, which will turn this into the series from k equals 1 to infinity of 2 to the k times a half to the k over 3k, which becomes the series from k equals 1 to infinity of 1 over 3k. And what do we know about this one? This one, we could state a couple different reasons why this might diverge. This diverges by, we'll just say, the p-series test. You could alternatively say like it diverges with a limit comparison with the harmonic series if you wanted, but just by the p-series test is plenty good enough. So your interval of convergence is negative 1/2, comma 1/2. Bracket on the negative 1/2, parenthesis on the positive 1/2. Good or no? All right. Let's see. Next part was part C. Use the second degree Taylor polynomial for f about x equals 0 to approximate f of 1/4. So in order to do that, we'll need to write our second degree Taylor polynomial, which, what was our series? It was k equals 1 to infinity of 2 to the k x to the k over 3k. Does that sound right? That's right. So our first term there should just be what we get whenever we plug in 1. And so if we plug in 1, we've got, we'll say the second degree Taylor polynomial at x is 2/3 x. And the second term when we plug in 2 ought to be, what is that, 4/6, which is another 2/3, so 2/3 x squared. And we want to approximate, what was it, the value was 1/4? Or was it a half? 1/4, okay. So we've got 2/3 times 1/4, and we've got 2/3 times 1/16. And then we'll just simplify that down to whatever that comes out to be. That's 1/6. What is that? Plus a 24th. Well, I wrote a 25th, but a 24th, which gives us 5/24. Good or no? Easy enough for that one. Okay. Then part D was about the Lagrange error bound. They specifically tell us that the absolute value of the third derivative of f is always less than or equal to 128/3 for all values between negative 1/4 and 1/4, which, since we're centered at 0 and we're approximating it at 1/4, that takes care of all the values between a and x. Right, there's our a and there's our x. And so it takes care of all those values. We know that the third derivative's largest possible value is 128/3. So our error our error, which is, you can write it this way, or you can write it as the second degree Taylor polynomial at 1/4 minus the true value at 1/4, should always be less than that. What was it, 128 thirds? Is that what it gave us, I believe? And then we've got a 1/4 to the third for our x to the third. And then all of that is divided by a 3 factorial. And so we'll just simplify all of that down. Somewhat unpleasant, but that's okay. What do we got? We got 3 factorial, that's 6, times the 3 is 18, times the 64, I don't know, 64, well, that's the 128, you cancel with that, so that becomes 2 over 18, which is 1/9, and I believe that's what the question was asking us to do. Yep, show that it differs by at most 1/9. So the Lagrange error bound, the error is less than this, which is 1/9, and that's enough to show it. Good or no? Any questions there? Any other particular types of problems you want to do, or should we do another series one? I always tend to gravitate towards the series because that's what people struggle with the most. I think I have one more series one here we could do, yeah. What do you guys think? Series, or anybody have anything else they'd like to look at? Another polar area, yeah. Let's see here. That might have been, that's not a polar area. I think that was the only polar area I had in these. So let me go back to the other. I can pull one real quick. I don't know if we did this one. I'm gonna put one in here real quick. Did we do this one in class? I don't think we did. Anybody remember doing this one in class? No? Okay, cool. Well, then let's do this one. So this is a calculator one. It's also got a little bit of like vector type stuff sort of in here, parametric type stuff in here. So that'll be a good thing to talk about too. So we got the polar curve r of theta equals 3 theta plus sine theta for 0 to 2 pi. We want to find the area in the second quadrant enclosed by the coordinate axes and the graph of r. So here's an instance where you might want to put your calculator into polar coordinates and graph this equation just so you know what it looks like. And just so that we have a general idea of what it looks like, I'll put it into Desmos and we can look at it. What was it? 3 theta plus sine theta, is that right? Do they ask us to do anything outside of the interval from 0 to 2 pi? Or even like 0 to just pi in the whole problem? Hopefully not. Just to make life a little bit easier. Okay. Thank you. I'm on the other page, so I can't actually see it. So here is just a very small version of what that graph looks like from 0 to pi. Pi is, obviously I let it go beyond pi, but pi, when we hit the x-axis there. Cool. So first off, we're going to find the area in only the second quadrant that's enclosed by the coordinate axes in r. So that means we're going to start with a, which is 1/2 of the integral from pi over 2, right, and pi, the bounds for our second quadrant, of 3 theta plus sine theta squared d theta. Good or no? And I don't know, I didn't pull up the guidelines for this one, but that comes out to be something. Everybody good? Anybody have a value for that? No? Okay, I got them up now. 47.513 it looks like. Everybody good with part A? I hope. All right, part B. Part B, from pi over 2 to pi, there's a point on the curve where the x-coordinate is -3. We want to find the angle theta that corresponds to point P and then find the y-coordinate of that. So if the x was the x-coordinate, right? The x-coordinate equals -3. Well, x, which is -3, ought to equal r cosine theta. So we need -3 to equal 3 theta plus sine theta times cosine theta. And so you will just solve that equation using your calculator to find out that that occurs at a theta value of, looks like 2.01692. And you don't want to round that because you need to figure out what y is, which is r times sine theta at theta equals 2.01692. And that comes out to be 6.272, which you can round to 3 decimals since that's your final answer. Any questions there on part B? All right. Part C. So for part C, we've now got a particle traveling along the curve, so that its position at time t is x of t, y of t, and we've got d theta dt is equal to 2. We want to find dy dt when theta is 2 pi over 3. So all of this is, related around really just the y value here. We don't really care what the x value is. We're really just talking about the y value. And so we should be able to set this up as dy dt, which is what we're looking. Is that what we're looking for? I think that's what we're looking for. Yeah. Dy dt is equal to dy d theta times d theta dt using the chain rule. And we should know what dy d theta is. And we should, I think they gave us d theta dt as 2. So our value of dy d theta is just the derivative of our y coordinate. So that's dy d theta, which you don't need to actually evaluate, at theta equals, I believe it was 2 pi over 3 times 2 equals our dy dt value. And it looks like that comes out to be -2.819. And I think it asks you to interpret it also. So you just say the y coordinate of the particle is decreasing at a rate of decreasing at a rate of 2.819, something like that. Does that make sense to everybody? Any questions on that one? All right. Somebody was asking also about maybe a regular area one. It's like something like this one. Because sometimes they do put just like straight A/B area questions on the BC test. This is all part of the curriculum anyway. So let's take a look at this one. Does that seem good to everybody? Everybody good with that? And let's see, this one is a calculator problem. So if we want to find the area of R, and we've got inverse tangent of x and y equals x squared, we just take our upper function. Well, first thing we need to do is we need to figure out where they intersect. So you'd write on the test inverse tangent x equals x squared, and you figure out that that occurs when x is, when does that occur? Obviously at the origin, right? And then also at x equals 0.833606 and x equals 0. So we are going to integrate the upper function inverse tangent x minus the lower function x squared dx from 0 to 0.833606. And that comes out to be 0.122. Everybody good with part A? Okay. Part B, we want the volume of the solid generated if we revolve R around the x-axis. So we're going to go around the x-axis. We're going to get washer cross sections that have a thickness of dx. So this ought to be pi times the outer radius. And what's our outer radius? It's the upper function, right? So pi times the integral of inverse tangent of x squared minus your inner function, which is x squared dx, and we're going to still integrate from 0 to 0.833606. And that comes out to be 0.230. And just a bit of caution, make sure you do outer radius squared minus inner radius squared. Don't do outer radius minus inner radius and then square it, right? Make sure it's outer radius squared minus inner radius squared. Don't forget the pi out in front. And even if you write the pi out in front, it's very common for people to forget to multiply their integral by pi once they've done the integral on their calculator. So don't forget the pi that's out in the front. Put the pi there, make sure you multiply by the pi. Good? Okay. Then for part C, we've now got region R, which is the base of a solid. The cross section is perpendicular to the y-axis, so perpendicular to the y-axis. That's important for us to note, is a rectangle with its height is twice the length in the base. So there's the length, this is 2L. So in order to figure out what our area is, we're going to have to do 2L times L. So our area is going to be 2L squared. And since the thickness of each of those cross sections is in which variable, what direction? Should be a dy instead of a dx like we often get because these are perpendicular. Okay, I drew that perpendicular to the y-axis. Those are perpendicular to the y-axis. The thickness of each one is dy. And so we had to do everything in terms of y, which means we need to figure out what 2L squared is in terms of y. Well, L itself in terms of x is it's x2 minus x1. It's the x coordinate from x squared, and then it's the x coordinate from here. And so we need to figure out what each of those x coordinates is. Well, if y equals x squared, well, it's on the next page. If y equals x squared, then x equals square root y. And if y equals inverse tangent of x, then x equals the tangent of y. And so our area ought to be 2 times our furthest right one, which was root y, minus our furthest left one, which was tangent y, squared. Everybody good with that setup? And then we will integrate from 0, and put the 2 out in front, root y minus tangent y, squared dy, and we still need to find this upper limit. So we found the x coordinate at which those intersect before, but now we need the y coordinate of which those intersect. So this value here comes from 0.833606 squared. Right, that's the y value when we have x squared there. And that value comes out to be 0.694899. And if we do all the integration there, this final value comes out to be 0.050. Everybody good with that? I think that's a good one for the cross-sectional area. We haven't done one of those in a long time. Good or no? All right. Anybody have anything else in particular that they want to go through? A tricky related rates one. Let's see here. Tricky related rates. Like actually like related rates, or just like a rate FRQ in general? Okay. Let's see if I can find a related rates thing in here. I mean, we did sort of did one a minute ago, but Let's see. I don't see one in here with related rates. They don't show up a ton. I know of one. Where is that one? Give me 1 second, and let me see if I can pull one up. I think I have one. While I'm doing that, Ben, I would say more often than not, the polar area problems show up in the calculator section. But there have been ones in the no calculator section, I believe, if I'm remembering correctly. Generally, though, yeah, they're more often those are in the calculator section. Let's see here. Okay, give me 1 second. There's a specific one that I'm remembering that's got a related rate part to it. And as I'm going through some of the old area and volume ones, yes, there are some polar areas that are non-calculator that I see in here. More of them, though, are the calculator ones, like I said. All right, maybe it's just this document. Give me 1 more second here. If I don't find one good in just a second here, I'll come up with something else for us to do. Okay, here's one we can do. I wouldn't necessarily call it tricky, but it is a related rate question, and And it also includes some area and volume stuff. So I don't believe we did this one. Have we done this one in class? I don't think we did. Like a funnel and stuff. This will probably be the last one we got time for. That look like one we did together this quarter? Okay, cool. All right, yeah, let's do this one. This one's definitely got, it's got related rate stuff. So wasn't the one I was thinking of, but then I saw it and remembered it. So perfect. Cool. So first part here, well, look at it for a second. We got a funnel. It's got a radius. It's got a height. It's got circular cross sections, which means, you know, one piece of it's revolved around the y-axis, potentially if we need to use that later. And at a height of h, the radius is this function here. So first off, we want to find the average value of the radius. Well, to find the average value of anything, any continuous function, we just integrate from 0 to 10, and then put a 1 over 10 minus 0 out in the front of that function. So 1/20th of 3 plus h squared dh. You can pull your 1/20th out with that 1/10, so you got 1/200th. And then you got 3h plus h cubed over 3 from 0 to 10. And you know, plug in your 10, plug in your 0. You got 1/200th of 30 plus 1,000 thirds. And I don't know, what does that come out to be? 30 plus 1,000 thirds with a, that's going to be 600, but I should do that. Looks like that comes out to be 109 over 60. Hopefully my arithmetic there is correct. I don't know if it says indicate units, but I'm going to put them there. It's inches. Everybody good with part A? Okay. Part B, finding the volume of the funnel. No. Our volume ought to just be pi times a function that represents the radius squared, right? Because that's effectively what we're revolving around the h axis here, right? We're revolving some function with this r value, and they've drawn r this way, but it could be this way too. It doesn't really matter. So we're going to integrate from 0 to 10 of our radius 1/20th 3 plus h squared dh. And if we want to, pi over 400 integral 0 to 10 of 9 plus 6h squared plus h to the 4th dh, and then a bunch of arithmetic there afterwards to come up with some answer. Do you guys want me to do the arithmetic on that, or everybody good with the setup there? And then, so then the related rate part of it here is in part C. So we've got the funnel's got a liquid that's draining from the bottom at the instant when the height is h equals, when the height is 3, the radius is decreasing at 1/5 of an inch per second. So first thing we'll write out is that we know that we're interested when h is 3, and we know that dr dt at that point is not 1/5, right? Dr dt at that point is decreasing at a rate of 1/5 of an inch. So dr dt is negative 1/5. Okay? And then all we got to do then is go in with our r function and take the derivative with respect to t of both sides of that. So we've got r equals 1/20th of 3 plus h squared, giving us dr dt equals 1/20th of 2h dh dt. And we are given h equals 3. We're given dr dt equals negative 1/5. I simplified the 2 over 20 to a 1/10 with our 3 there. Our dh dt looks like that comes out to be negative 2/3. And I don't know if they wanted units, but it's just per second. And I would say that in the free response, the related rates don't usually get much more difficult than that. They often show up, I mean, look at it, I won't say often. The general place that you might see a related rate within the free response is within the area or the volume question. So usually it's a part C. So, you know, this one, or we did the one a little bit ago with with part C here. So we had a little bit of a related rate thing going on there. So that's where you might see them coming in, as part C of the area and volume questions. Everybody good with that one? I know it wasn't a tricky one, but at least it sort of reminds us a little bit about how to do them. And usually they're just, you know, take the volume formula you got or take the equation that they gave us and use that for your related rate. All right, before we finish, because I don't think we got time to really go through any more problems here, before we close up and call it a day, I just want to really quickly, I'm going to pull up a document here that's in Google Classroom. I believe it's in Google Classroom. I'm scrolling through. No, maybe it's not. Thought I had it in Google Classroom. Oh, I guess I don't. All right. Well, I'll make sure that it's up in Google Drive here in just a second. It should be up in Google Drive. Give me a second. I thought it was in there. All right. So this, which I know says AB, but these all pretty much apply to BC also. So can you guys all see this thing? Okay.
Yeah, we can see.
You can? Okay. So first off, don't round until your final answer. On calculator questions, write out all the decimals until you get to your final answer. Use, if it gives you 6 decimals, which is usually what it gives you when you're looking for like an x-intercept or something on your calculator, write out all 6 decimals, use all 6 decimals. You can store the values in your calculator if you want, if you know how to do that, or I mean, it's easy enough. You just type in the number, and then in the bottom left, I believe it's the bottom left corner, there's a button that says STO with like a little triangle or an arrow on it. And then you can choose a variable to store that as. So you can hit alpha A or alpha B, or you can store it as the value of X or whatever you want. And then just type in the X or the A each time you need it. So don't round to your final answer. I know I've said this before, but like if you can't do part A, that's fine. Go do parts B and C. If part C requires an answer from part A, do something, you know, that makes, even if it doesn't make any sense, do something that looks like calculus in part A to get an answer. Use that answer from part A for your work in part C, where you needed an answer from part A. And you're likely to at least get some of the points for part C. Anytime you're using your calculator, make sure you write out what you're having the calculator do. So if you're having it solve an equation, write the equation. If you want to know where sine x intersects with tangent x, you know, write sine x equals tangent x. Then use your calculator to figure out where that happens and put the answer. If you need to find the value of a definite integral on a calculator section, don't try and do it by hand. Just write out what the definite integral is and then put the value of it from your calculator. Same with the value of a derivative of a function on the calculator section. Don't take the derivative of some awful looking function that they've given you. Just write the derivative equals, you know, write f prime of 7 equals and put the value. So make sure you use your calculator for what it's there for. And down here a little bit further, which I'll go back up and talk about the other ones in a second. On the FRQs, on the free responses, don't use your calculator for anything except these 4 things. Graphing, finding derivatives at a point, finding definite integrals, and solving equations. Okay. They want to see calculus work. Obviously, if they want to know the max or the min of some function and they're giving you a calculator, you can graph the function and find the max or the min of it, right? But they want to see that you did the calculus correctly. They want to see that you found the derivative and set it equal to 0 and found the max and the min that way. Right? You can use your calculator to check and see if you were right. That's great, do that. But don't just put what the value is without any calculus to back it up. Same with if it asks about concavity or points of inflection or when it increases or decreases or domain or range or any of those things. You have to show the calculus work behind it. And then you can check your work using the calculator if need be. This one here, don't waste time erasing bad solutions. This is good. So like if you do part A and you think it sucks, and you want to move on to part B and C because you know how to do those and you're not sure how to fix A. Okay, great. Don't erase part A. Just do part B, do part C. When you have time to come back to part A, leave what you wrote for part A there. You're going to have lots of space. And then off to the side, try and do some better stuff for A. If you decide that what you did was better the second time around, then just put a big X through what you did the first time. Okay? Don't bother erasing it. That just wastes your time. Right? And it takes a lot less time to just draw an X and you save yourself 20 seconds. Okay? If what you did the second time on part A is worse than what you did the first time, then just put an X through that and keep what you had before. Don't just erase a bunch of stuff though for no reason. Leave something there because there might be some piece of what you did that is worth 1 point. And you want that point rather than not getting that point, obviously. Be extra careful with your reading comprehension. Okay? Make sure you answer what it asks. If it says, when does the function have a maximum value, you should be giving an X coordinate. If it says, what is the maximum value, you should be giving a Y coordinate. So make sure you actually answer the question. Okay? When you justify something, do a good job. Use math words. Use your theorems. If you're using theorems, make sure you state the initial conditions of the theorem. So if you're using the intermediate value theorem, you need to state that the function is continuous on the interval from A to B. If you're using the mean value theorem for derivatives, you need to state that the function is continuous and differentiable on the interval from A to B. And so make sure you state those things. Make sure that they're true also, but make sure you state them. Yeah, okay, it says that this one is whatever, you know, you make an educated guess before skipping a multiple choice question. That's all good. I'm sure you know to do that. My suggestion though is you're going through the multiple choice. If you come to one, you know, you do the first 5, they take you a minute or so each. Maybe that's great. Come to number 6, and number 6, you're like, oh crap, this is going to take me 10 minutes. Don't spend 10 minutes on number 6. Skip it. Okay? You know, circle something that maybe looks right so that if you have no time at the end, you can come back and just bubble something in that seems like it might have been right. But skip that problem. And then go do number 7, which is going to take you 30 seconds, and number 8, which will take you a minute or a minute and a half, and number 9, which takes 30 seconds. And go through all the quick and easy ones, and then come back and do the ones that are going to take you more time later. Every multiple choice question is worth the exact same amount. The exact same amount. They're all worth 1.2 points. So don't waste your time on one that takes 10 minutes and neglect doing 3 problems or 4 problems that take you less time later on because you run out of time. And so just skip it and come back to it later if you have time. It says relax and have fun. I don't know. I didn't write this guide here, so I wouldn't have written that. But I will tell you that you are all going to do wonderfully. You are all capable and smart individuals. You should have confidence in yourselves. Just, you know, get some sleep tonight, you know, study for a while later this afternoon, take a break right now, maybe study for another hour or 2 this evening. And you go to sleep, get up, go take the test. You'll be fine. Okay? I have faith in all of you. And remember, I will see your scores. So keep that in mind. All of these things are like errors of things not to do. I've talked about like a lot of these already today. Well, okay, maybe not a lot of them, but I talked about this volume by washers one, so don't make that screw up. I don't think you guys are making any regular anti-differentiation errors. I just give this to the AB kids mostly. Don't forget your plus C. Make sure if it's a separable differential equation, you separate the variables. And don't just assume that if the derivative is 0, it's a max or a min, or if the second derivative is 0, it's a point of inflection. You've got to actually check and show the change in concavity or the change from increasing to decreasing. And remember, the average rate of change, which they might ask you, what's the average rate of a change of function? What's the average rate of change of a function on an interval? Sometimes people like to do is like the derivative at a plus the derivative of b over 2. No, the average rate of change is just the slope, y2 minus y1 over x2 minus x1. So don't screw that up either. Let's see here. I can't think of anything else to remind you all of. Anybody have any more questions? I will put this document up in Google Drive and in Google Classroom also. I thought it was already up, but I guess it's not. Anybody else? Any other questions before we're done? And we're already over our time. So Ryan, I'll post the video up as soon as it finishes rendering through Zoom, which usually takes like 30 or 40 minutes for these 2-hour-long ones. And then it takes another 20 or 30 minutes for YouTube to like, process it. So it'll probably be up by like 3:30 or 4 is my best guess. I mean, I'll start doing it as soon as we're done, but it takes a while for it to do its thing. So, yeah. Anybody else? Any other questions? All right.